In this video, we're going to be talking about how to control hydrogel properties, and we're going to look at some quantitative aspects of hydrogel characterization. And finally, we'll wrap up the video with some examples of stimuli-responsive polymers, as well as special topics including molecularly imprinted polymer networks and interpenetrating polymer networks. So to begin with, when we talk about controlling hydrogel properties, what we're really talking about is controlling the porosity of those hydrogels and therefore the ability of those hydrogels to swell. Obviously, that has to do with the cross-linking density. The cross-linking density means basically how often do we have a junction point or a tie point in between polymer strands. So for example, here we have an example of a system that has a high cross-linking density versus one that has a low cross-linking density. Obviously, in this particular case, we have more junctions than we do on the right-hand side. And obviously, the higher the cross-linking density, the lower the porosity of the hydrogel system. One of the I guess variables that we talk about when we talk about porosity of a hydrogel is this epsilon, which is the mesh size of the hydrogel. So we don't normally talk about the porosity size or the pore size, but we talk about the mesh size for the hydrogel, and that's epsilon. And if you look at the plot down here at the bottom, as the cross-linking density increases, what we expect is that the mechanical properties of the hydrogel, such as the modulus and the stiffness, are going to increase. At the same time, as the cross-linking density increases, what's going to happen to the permeability, the water content, and the swelling ability of the hydrogel is that they're going to decrease. So obviously, the size of the mesh, which is directly related to the cross-linking density, is going to have a huge impact on the overall behavior of the hydrogel. The next two slides, or the next few slides that talk about the quantitative aspects of hydrogels, actually have the whole purpose is to be able to determine the mesh size. So we'll be talking about that in just a second. Another factor that can control the porosity of the hydrogel is going to be the comonomer composition. For example, if your hydrogel is made out of both hydrophilic and hydrophobic components, then changing the ratio of the hydrophobic to hydrophilic components will have a huge impact. The more hydrophobic content that you have, the less water swelling ability that hydrogel is going to have. At the same time, if your hydrogel is made from ionic polymers, the highest extent of swelling would be obtained if your ionic system is in its charged state and it's not neutralized. So if you have a polyanionic hydrogel that is chemically cross-linked, you're going to have a high swelling whenever the system is in its charged state. On the other hand, if you have something like a complex coacervate that has two different polyelectrolytes that are positively and negatively charged, then if you have 50-50 molar ratio of the two, you will likely have the lowest extent of swelling compared to if you had something like a 75% to 25% molar ratio of the two electrolytes. All right, the polymerization conditions can also play a role. The type of solvent is going to have an impact, first of all, by changing the reactivity of the monomers. So some monomers are going to be more or less reactive depending on what solvent they are reacting in, and thereby the polymer composition, like the actual hydrogel composition, might not necessarily reflect the composition of the monomers that you added into the reaction. At the same time, the type of the solvent will affect whether or not you have aggregation of certain components. For example, if a solvent that is not very good for one portion of the polymer system is utilized, then that polymer that is not well dissolved is going to try to aggregate. And so you might lead to a very non-homogeneous hydrogel where you have segregation of different types of polymers in different places. Finally, the amount of solvent is also going to play a role. if you begin with a very dilute solution of your either monomer or your prepolymers, then when the system is cross-linked, it is likely that you're going to have a higher porosity because all of the polymer chains are extended because they are kind of dissolved in very, they have space to extend. Compared to whether if you started with a very concentrated monomer or prepolymer solution, where likely you would have all of the molecules kind of intertwined and you would lead to more entanglement in between the chains, so more physical cross links. In addition, if you have a very dilute system to begin with, some of your cross linkers might actually form cycles and kind of link to themselves by both functional groups at the ends linking to themselves instead of actually cross-linking different polymer chains. So obviously, if you have a very dilute system, you might actually end up having a lower cross-linking density than what you expected. All right, in the next few slides, we're going to be looking at the quantitative description of hydrogels. We're going to start talking about how it is that we look at the ability of these hydrogels to swell. And then based on that theory, we're going to look at the equations that have been derived in order to calculate the molecular weight between crosslinks from which we can obtain the mesh size of the hydrogel. So let's get started. Oops. All right. So the theory behind hydrogel behavior and hydrogen swelling was developed by Fleury and Huygens. And basically it says that the ability of the hydrogel to swell is controlled by two factors. The first factor is the elastic retractive forces that are associated with the crosslinks in between the polymer chains. And that is competing with the thermodynamic compatibility of the polymer with the solvent, which actually would lead to the mixing of that polymer in the solvent. So basically, if you have good compatibility between the polymer and the solvent, the polymer chains are going to try to dissolve in the polymer and expand in the polymer to infinite dilution. And that's what we talk about mixing. So you can see that the two things are kind of competing against one another. The number two, it's leading to the polymer chains to disentangle from one another and instead encourage interactions between the polymer and the solvent, while number one has to do with the retractive forces that are keeping those chains together. All right, so in terms of free energy, we have that the Gibbs free energy associated with the whole hydrogel behavior is going to be equal to the Gibbs free energy associated with the elastic component plus the Gibbs free energy associated with the mixing between the polymer and the solvent. We can then put that same concept in terms of chemical potential, where the chemical potential is the change in the Gibbs free energy with respect to a change in the amount of component. Basically, the amount would be the moles of the component. And that chemical potential is at constant temperature and pressure and is represented by the letter mu. So here we have the change in the chemical potential, which is associated with the chemical potential of water within the gel minus the chemical potential of free water. And that's going to be equal to the change in the chemical potential associated with the elastic component of the hydrogel plus the chemical potential associated with the mixing of the polymer and the solvent. We know that at equilibrium, the Gibbs free energy is equal to 0. And so we can set the left-hand side of this equation also equal to 0. And because of that, what we have is that the basically the elastic and the mixing contributions are going to balance one another, or basically they're going to add up to 0. And the next part is actually the equations that have been derived in order to calculate the chemical potential associated with mixing or with the elastic component of the hydrogel. So for mixing, we have this equation that says that the change in the chemical potential associated with mixing is going to be equal to R, which is the gas constant, times T, which is the temperature in degrees Kelvin, times this parenthesis that includes the natural log of 1 minus nu 2s, where that is the polymer volume fraction of the gel, which is calculated by this equation down here, which basically means that we're going to be taking the volume of the polymer divided by the volume of the swollen gel, or Vp divided by V of the gel, and that's something that can be experimentally determined. If we continue with the equation, we can see that the other parameter that we have is this chi1, which is basically the polymer water interaction parameter, also known as the fluorine interaction parameter. And that one has a value of less than 0.5 if the water is a good solvent for the polymer, or greater than 0.5 if it is a bad solvent for the polymer. Now, I should mention that these equations are typically utilized for hydrogels that are prepared in the absence of another solvent. Basically, all that we have is monomers that are liquid, which are then cross-linked and polymerized into a solid system that can swell in water. So let's just leave it at that for now. All right, so from here, basically, again, this equation will be utilized to calculate the chemical potential associated with the mixing of polymer with the water. Here at the bottom, we have the equation to calculate the chemical potential associated with the elastic portion, and that's also equal to RT times VE. VE is the effective cross-linking density of the hydrogel, which is equal to nu n, which is the effective number of polymer chains in the network, divided by V0, which is the polymer unswollen, the volume of the unswollen polymer. I should mention that this VE is very important because within it, within the calculation of this VE, is where the molecular weight between crosslinks comes into play. And so really we're going to be utilizing these equations, putting them into this equation and solving for VE, where VE is going to have within it the molecular weight between crosslinks. I should come back to here. Here V1 is the molar volume of water, and the molar volume of water is basically equal to 18 milliliters per mole, or 18 centimeters square per mole for water. And everything else in the equation has already been defined. All right, so again, we're going to be taking those two equations and setting them into this equation, and then solving for the new E, which includes the molecular weight between crosslinks. Now, from those equations, we can determine the molecular weight between crosslinks, which is M sub C, which is basically defined as the name implies the molecular weight in between two junction points. And those junction points could be chemical crosslinks, or they could be physical crosslinks as well. So it doesn't matter which type of crosslink we're talking about here. All right, so the equation that we get from the previous two slides is this one that says that 1 over the molecular weight between crosslinks is equal to all of this. In this equation, the new variables that appear are Mn, which is the number average molecular weight of the uncross-linked polymer, which means that experimentally, you would carry out the same experiment as for preparation of the hydrogel, but in the absence of the cross-linker. And so, for example, you would do the free radical polymerization of, let's say, acrylamide, but in the absence of the bisacrylamide, in order to see with the conditions that you used, what polymer chain length you would get. And you would characterize that M sub n utilizing something like gel permeation chromatography, for example. Let's see, what else do we have that's new here? This right here is the specific volume of the polymer, which is defined as 1 over the density of the polymer. The V1 we already defined as the molar volume of water, which again is 18 centimeters cubed per mole. The new 2S is still the polymer volume fraction in the swollen state, which again is determined experimentally by figuring out the volume of the polymer. Actually, I will talk about how to measure this on the next slide. And then chi, we already mentioned that that this is the polymer water interaction parameter, which is a value that can be found typically in the literature. All right, this equation is known as the Flory-Renner equation, and it is developed for hydrogels that are prepared in the absence of solvent, meaning that again, we're starting with just monomers that are liquid or prepolymers that are liquid and that are cross-linked into the form of a hydrogel in the absence of a solvent. Now, the next equation, which is right here, is a derivation from the Flory-Renner equation, and this is known as the Peppas-Merrill equation. This equation accounts for the inclusion of a solvent, for the presence of a solvent. So for example, you might begin with monomers, whether those monomers are liquid or solid, but all of them are diluted in a solvent in order to get a more porous hydrogel system. So the equation is actually very similar to the one that we had in the previous slide, but now we have a new set of variables that are down here, which have to do with the volume fraction of the polymer in the relaxed state. And this relaxed state is basically the state of the hydrogel in which it is as soon as it is prepared. So the way that the experiments are done are that typically you would prepare the hydrogel, um, and immediately after the hydrogel is prepared, you would carry out some measurements. You would actually come and measure the weight of the hydrogel in air in that relaxed state and the weight of the hydrogel in hexane in the relaxed state. You would then take the hydrogels and you would dry them, typically by placing them in an oven, maybe under vacuum, maybe under a little bit of high temperature. And once the hydrogel is dried, you would come and measure the dry weight. So the dry weight of the hydrogel in air, the dry weight of the hydrogel in hexane. And then after that, you would put the hydrogen, and actually I should mention that those two also come into this equation. This is the dry state and dry state. After that, you would take the dry hydrogels and you would put them in the swelling buffer, whether that's just water or phosphate buffer saline or another buffer at a specific pH that you want. And you would measure the same two things for the hydrogel in the swollen state once it has reached equilibrium. What you measure is the weight of the hydrogel in air in the swollen state and the weight of the hydrogel in hexane in the swollen state. From that information, you now are able to calculate the the polymer volume fraction in the swollen state and the polymer volume fraction in the relaxed state, which are the two variables that are going to go into this equation. At the same time, you would go and look on the literature for the value of the Flory interaction parameter between the polymer and the solvent, and you would look up information or you might measure information about the specific volume of the polymer. That can be, for most part, you can find it in the literature. If you were to calculate it yourself, what you would do is that polymer volume or polymer specific volume is equal to 1 over the density of hexane times, and I know that I have a mistake here, so let me go ahead and correct that. This right here is supposed to be the weight of the polymer in hexane in the dry state. Sorry about that. All right, so anyways, you would take the polymer and you would do this calculation of 1 over the density of hexane times the weight of the polymer in air in the dry state minus the weight of the polymer in hexane in the dry state divided by the weight of the polymer in air in the dry state. Now you might be wondering, why is it that we're measuring things in hexane? So what we're doing is that we're utilizing Archimedes' principle of buoyancy, where the buoyant force is going to be equal to the weight of the displaced fluid. And the reason why we're doing that is we're trying to remove the we're trying to figure out what fraction of the weight is associated with the polymer versus that which is associated with the buffer or water that has been uptaken into the hydrogel. And so this principle allows us to do that. Typically, these measurements are done utilizing a hanging basket apparatus that enables us to place the hydrogel in hexane without actually submerging it all, and being able to measure that weight in the hexane. All right, so using all of this information, again, we're able to calculate the molecular weight between crosslinks, which is N sub C, which is directly related to the mesh size of the hydrogel, and which plays a critical role in the function of the hydrogel, because it would determine how much your hydrogel can actually swell and what size of drugs or cells you might be able to encapsulate within, and what type of mass transport could occur between like salts and physiological fluids in that hydrogel. So that's hugely important. If we go to the next slide, it basically summarizes the two equations, the Fleury-Renner, which is for neutral hydrogels prepared in the absence of solvent, and then the Pepys-Merrill equation, which is for neutral gels prepared in the presence of solvent. From there, now we go to the calculations for ionic gels. So for ionic gels, now we have one more component. So no longer do we just have the elastic component and the mixing component. Now we also have an ionic component, which has to do with the ability of that hydrogel chain, of those hydrogel chains, to repel one another as a function of charge, right? As we know, if the hydrogel polymer system is in its charged state, what we're going to have is repulsion in between the chains and thereby swelling. That swelling would be, for an anionic hydrogel, for example, below the pKa we would have no charges, but once we reach to the pKa, there's going to be deprotonation leading to negative charges that repel one another and lead to high swelling at high pH. On the other hand, for a cationic hydrogel, initially at low pH, the system is in its charged positive state, meaning that the gels, the polymer chains would repel one another and you would have high swelling. Once we get to a pH that is near the pKa, you would have deprotonation again, which in this case leads to now a neutral system, which no longer repels, has repulsion between the chains, and thereby now the swelling subsides. So anyways, coming back to the equation, we now have the ionic term for the chemical potential. That chemical potential can be calculated using this equation, where the delta C is equal to the difference in the total concentration of mobile ions in the gel, and is strongly dependent on the ionic strength of the medium, meaning the solution that you utilize for swelling the hydrogel, and on the nature of the ions that are present. From here, we go to an equation that has been derived from that to be able to calculate the molecular weight between crosslinks, which is hidden right here in the equations. And obviously these equations are quite complex and makes it kind of hard for us to calculate. But basically we have two equations, one for anionic gels, one for cationic gels. The equations have the same variables as the previous two equations, except that now we also have the variable I, which is the ionic strength of the solution in which you are swelling the hydrogel. And then we also have Ka and Kb, which are the acid or base dissociation constants for the polyelectrolyte that is making up your hydrogel. These equations are known as the Brannon-Pepys and Pepys equations. Again, they will be utilized to calculate the molecular weight between crosslinks. All right, so coming back to how do we utilize the molecular weight between crosslinks in order to calculate the mesh size. Remember that the mesh size is represented by this epsilon, and notice the equation now that we have the molecular weight between crosslinks being proportional to the mesh size in a way. So in this equation, our nu2s is still the volume fraction of the polymer in the swollen state. C sub n is the polymer characteristic ratio, which is a variable that can be found in the literature for a range of different polymers. And M sub r is the molecular weight of the repeat unit of the polymer. For example, for polyethylene glycol, it would be 44. And now, I'll just leave it at that. The top equation is not really that important because this is what you would actually be utilizing in order to measure your mesh size after calculating the molecular weight between crosslinks from the previous equations. All right, so from here we move on to hydrogel applications. So as we all know, hydrogels can be utilized for contact lenses, drug delivery systems, tissue engineering scaffolds, wound healing matrices, and blood contacting systems. They can also be utilized as kind of capture materials for biosensors. They could be utilized also as kind of transducers for transducers for biosensors or for oh god, what do you call this? I'm drawing a blank here. Valves for microfluidic systems. That's what I was trying to get to. So there's a number of different applications. And of course, in all of these applications, what we're using is the porosity of the hydrogels, which enables us to load agents. It enables us to have high transport of physiological fluids to enable us to maintain viability of cells. We're also utilizing the cytocompatibility of the polymers that are utilized to be able to maintain cells, maintain humidity, of course. And so, yeah, hydrogels have a number of applications in biomedical purposes. And some of them are listed here again. We can use them for the delivery of cells and tissue constructs to the body. We can use them to direct and provide therapeutic assistance for wound healing purposes. And the advantages that we utilize are the fact that hydrogels have a high content of water that can maintain the viability of cells and fragile drugs such as proteins or oligonucleotides. They have good transport for nutrients and for metabolites to be able to come in and out. They can be easily modified to include cell adhesion peptides, as we already talked about. Some of them can be injected as liquids that would then gel inside of the body by utilizing temperature responsive systems or utilizing polymerizations that can be activated in situ either by temperature or with the use of photocatalysis. And then the disadvantages of the hydrogels are that they can be typically very hard to handle. Again, think about them like jello. It's very fragile. It can be squished very easily or it can fracture very easily. They are mechanically weak. They might be difficult to load with drugs and cells and then cross-link. I would go ahead and mention that cells are quite large. They're in the order of 10, 20, 30 micrometers in size. The mesh side of the hydrogels is never going to be that big. The mesh size is going to be typically in the order of a few angstroms, maybe 10, 20 angstroms. And so they're a lot smaller. The mesh size is a lot smaller. So the gels would be kind of entrapped within the hydrogel itself, right? But still it would be porous enough to enable soluble molecules to be able to come in and out of through those pores. All right. Another disadvantage is that they might be difficult to sterilize because of the fact that they are three-dimensional networks, and you have to make sure that not just the surface is sterile but the inside of the hydrogel as well. We already talked about stimuli responsive polymers, and of course we can apply or we can utilize those polymers in order to make stimuli responsive hydrogels. For example, we can make hydrogels that respond to pH by utilizing polyelectrolytes, either through the coacervate method that we discussed or the ionotropic gelation method that we discussed, or even you could utilize a pH responsive polymer that is chemically cross-linked as well. And so of course with pH change there's going to be a change in the ionic character of the polymer, which would result in charges that repel the chains from one another and which would lead to swelling. And that is a reversible process, so we can change the pH back and forth to change the porosity of the hydrogel back and forth. Similarly, we could utilize temperature responsive polymers to create temperature responsive hydrogels, and those can be activated either externally by changing the temperature, maybe with a pad that increases the temperature locally, or by utilizing metal nanoparticles that enable us to use lasers to irradiate the nanoparticle and lead to localized heating within the hydrogel, which would then lead to swelling. And again, this is another reversible process that can be utilized to heat the hydrogel back and forth and change the porosity of the hydrogel. Similarly, we could utilize degradable polymers within the hydrogel. And of course, we had talked about all of the polyesters that are degradable. And I'll go ahead and mention that most of the polyesters are also hydrophobic. And so to include them in hydrogels, they would have to be part of like a tri-block copolymer system where you have a high, let's say, polyethylene glycol content, but you would have short parts of the polymer that have that polyester that is degradable. Um, or you might have the crosslinker contain that polyester, but then the rest of the hydrogel be a hydrophilic polymer. Of course, the degradation by hydrolysis is not reversible, so you would just have kind of degradation in one direction. All right, we also have, or here I have an example of pH responsive polymers. Remember that pH response can lead to hydrolysis, which is the degradation that we mentioned in the previous slide, or it would lead to a change in the ionization of the polymer chains, which ionization meaning the charging is going to result in higher solubility and swelling or dissolution of the system. And one example is the hydrogel made from itaconic acid that I mentioned before. This was one of my publications where we clearly saw the swelling ability of these hydrogels as we increase the pH above the pKa of the itaconic acid. Of course, that hydrogel needs to contain not just the ionic monomer, but also a cross-linker at the very least. And in this case, it also included polyethylene glycol methyl ether methacrylate, which could hydrogen bond with the protonated itaconic acid in this range in order to lead to very shrunken gels at the low pH. This is the same example just to show you at low pH, a pH less than the pKa, we have the itaconic acid in its neutral state, protonated state, where we have the carboxylic acid with the hydrogen. And in this particular case, that protonated carboxylic acid can hydrogen bond with the polyethylene glycol from the PEG-MEM macromer, leading to a very collapsed state that enabled proteins to be protected from the low pH of the stomach. But then once the hydrogel would go into the intestine, where the pH is greater than the pKa of the itaconic acid, that itaconic acid would now deprotonate and basically have a charged state where we lose the hydrogen bonding ability. And in addition to that, now we have repulsion between the very many itaconic acid repeat units, leading to swelling of the hydrogel and thereby increase in the mesh size of our system. Using that itaconic acid hydrogel system, we were able to show increase in the swelling with an increase in pH as expected. And in this particular case, I wanted to show you this because what we can see is the swelling extent as a function of cross-linking density. So in this particular case, I included two different amounts of cross-linker in the hydrogels. And as expected, the less cross-linking density that you have, the more swelling that your hydrogel can achieve. Here I have an example of temperature responsive hydrogels. In this case, these are hydrogels that were made with polyethylene glycol macromers. So these are pre-polymers that have the ability to be further polymerized, something like a polyethylene glycol methyl ethyl methacrylate. together with N-isopropyl that provides the temperature responsiveness. Remember that N-isopropyl leads to a polymer that has LCST behavior, meaning that we have aggregation of the polymer as the temperature increases above the LCST. And the LCST for N-isopropyl is in the order of 32 degrees Celsius, more or less. What you can see is that the resulting hydrogel system basically shrinks as we increase the temperature in this particular case, and basically at physiological temperature it would be almost in the shrunken state, which means that we can initially load the hydrogel with insulin, in this case at room temperature, and then once that system is injected into the body, it would be in the shrunken state, being able to kind of preserve the insulin and maintain its stability. And that's what's shown here on the right hand side. So this is a control where the insulin is not protected by the hydrogel, and we can see that the insulin remaining has decreased to 0 within about 5 hours. On the other hand, the insulin that is maintained within the temperature responsive hydrogel can last for much longer time period. So about 80% or more of the insulin is retained in its active state within the hydrogels that have been made with this temperature responsive system. All right, now I wanted to talk a little bit about interpenetrating polymer networks. So here's a really good figure of an interpenetrating polymer network. We have two polymer networks. One of them is, I think it was polyacrylamide. The other one is polyacrylic acid. The two of them are completely independent. If you can see, they are intertwined within one another, but they are not actually chemically reacting with chemically covalently attached to one another. The way that we can prepare this kind of interpenetrating networks is by either sequential polymerization of one monomer in the presence of the second monomer. For example, I could polymerize polyacrylamide first, let's say the yellow network first, and then I swell that network in the monomer for the second, so in acrylic acid for the second polymerization. I then polymerize that second monomer in the presence of the first polymer network, and so I would end up with this kind of intertwined polymer system. Another way to polymerize these systems is to do concurrent polymerization using different mechanisms of polymerization. So for example, I could use free radical polymerization for one of the polymer networks, and I could use one of the bioorthogonal chemistries for the other polymer network. And the two chemistries would be independent of one another and thereby not end up cross-linking with one another, yet they would be intertwined, and so they can actually do not diffuse from one another. These kind of polymer systems are really interesting in that they are they can swell, but they will not drift apart, and you get very interesting behavior because each of the polymer provides their own behavior. Like how can I explain this? So for example, if you have temperature responsiveness in one of the polymer systems, that temperature responsiveness would not be affected by the presence of the other one. Or if you have an ionic character, then that the ability of that polymer to become charged with pH would not be affected by the other polymer system. Yet, since they are intertwined, they cannot diffuse from one another. So they provide kind of very interesting properties. All right, the last topic that I wanted to mention are these molecularly imprinted polymers. So they are abbreviated as MIPs for molecularly imprinted polymers. And basically, these systems are synthetic polymer networks that are generated in order to create affinity materials. So earlier in the previous video, we talked about the fact that we could cross-link a hydrogel utilizing affinity interactions. In this particular case, I'm talking about actually making a hydrogel that would have affinity towards certain molecules. And basically, we're making this hydrogel act as a synthetic antibody or as a synthetic aptamer, in that we're providing the hydrogel the ability to recognize particular molecules. And of course, this is going to have applications in a number of areas, including chromatography, where we want to be able to separate certain molecules from from a mixture of a number of molecules. We could utilize these molecularly imprinted polymer networks for drug delivery, in that they would create, they're basically a hydrogel that has high affinity for a particular molecule, and so it would be less likely to allow that molecule to diffuse away, because we have the right chemical environment for that molecule to stay. Or we could utilize them for sensor actuators, where the affinity between the biomolecule and the polymer network enables us to trap certain molecules and provide some kind of change in the system, such as swelling or shrinking, that then can be utilized for biosensing. All right, so how do we actually make these molecular imprinted polymers? Well, what we're going to do is that we're going to take the biomolecule of interest, and we're going to analyze it to understand what kind of chemical moieties does it actually present on its surface. Based on the analysis, we're then going to select or synthesize specific monomers that might have some affinity to this molecule. For example, if this molecule contains a lot of positively charged groups on its surface, then we might choose monomers that have negative charges that would have some affinity toward it. Or if this molecule has a hydrophobic pocket, then we might choose some monomers that are hydrophobic that we think can fit within that hydrophobic pocket, so that they can have some affinity. We then put together the biological molecule together with the monomers that we have selected, as well as a cross-linker. We go ahead and allow them to interact for some time, where now the molecules that we thought would have some affinity to that molecule will actually come in and bind to it through through secondary interactions, basically through non-covalent interactions. We then go ahead and carry out the polymerization by addition of an initiator and an activation of that initiator, I should say. And so now we're going to get a system that is polymerized. And in this particular case, they were showing us these are supposed to be vinyl monomers. Notice that they contain that carbon-carbon double bond. We have two different types of monomers, one with a round and one with a arrow. Once they have interacted with the biological molecule, they basically form these complexes that then can be polymerized with the cross-linker into now having a hydrogel, where the biological molecule of interest is kind of part of the hydrogel through those secondary or non-covalent interactions. After that, we would wash away the molecule of interest, and what we're left with is a hydrogel that has the pockets that have the right size and the right chemical moieties to interact with high affinity with the molecule that we are interested in. And so this now could be utilized for trapping the molecule from physiological fluids, or for loading a drug. Basically, that biological molecule would have to be the drug, and now the drug would have less desire to leave from that hydrogel, if you would. Another representation of this same concept, oops, sorry about that, can be seen on the next slide. I really like this graphical representation, where again the yellow molecule is the biomolecule of interest to us. We investigate, we study basically what does the surface of that molecule look like, and what kind of chemical entities would have high affinity to it. We then put those monomers together with that biological molecule and allow them to interact. We also include a cross-linker that is bifunctional. We then polymerize the whole thing into now making a hydrogel. This is supposed to represent a hydrogel, where notice that we still have a pocket that has the right that contains the biological molecule bound with those monomers that we selected. And once we wash off the biological molecule, we're left with the pocket that has the right size, the right electrostatic environment, and right hydrophobic content to be able to enable further binding of that molecule should it come into contact with it again. So these molecularly imprinted polymers are quite interesting. And the next slide is to show you an example of those molecularly imprinted polymer systems, in this case in the application of drug delivery. All right, so the idea here is that we want a hydrogel that can bind to hyaluronic acid, which is shown here on the left. And so to do that, what they did was to investigate the structure of a hyaluronic acid binding protein, which, if I remember correctly, is called CD44. And let me double check on that. Let me go and find my slides. Yes, CD44. So what they did is that they investigating all of the peptides on that protein, and they found that the ones that are orange and pink were very important for the ability of that protein to bind to hyaluronic acid. So basically orange and pink are in this region. And they identified that the repeat units or peptides that were the most important were asparagine, tyrosine, and arginine. These three are part of that protein. And so based on that, what they did is that they selected synthetic monomers that have similar functionality to the peptides that they identified as critical. So for example, instead of using asparagine, they utilize acrylamide, which can be polymerized by free radical polymerization, yet it contains this amide group that the asparagine also had. Similarly, instead of using tyrosine, they selected N-vinyl pyrrolidone, which is a molecule that has a similar cyclic structure, and it also has hydrogen bonding capability. And finally, instead of arginine, they utilized diethylaminoethyl methacrylate, which also had positive charge, just like asparagine would have under physiological conditions. So then they took these three monomers together with a crosslinker and they generated a hydrogel in the presence of hyaluronic acid. And what they were able to do is to be able to show this, show the release of hyaluronic acid over time. In this particular case, this is the system that is, oh shoot, I forgot now. But what I would say is that the ones down here are the ones that are utilizing the molecularly imprinted polymer that would delay the release of hyaluronic acid from the system. While if you have less of those functional monomers, the hyaluronic acid would be able to leave the hydrogel faster because there's less affinity for hyaluronic acid. So that is that. All right. And that completes